surpassing $300 billion annually. The frozen food industry has risen to become one of the most powerful sectors in the world, turning frozen products into one of the most formidable profit engines on the planet. But have you ever wondered how more than 200 million tons of frozen food each year are actually produced to serve a world increasingly dependent on convenience? In today's video, Agriculture Insight takes you inside some of the most advanced factories, where machines turn time into an advantage, where freshly harvested ingredients are processed and their freshness locked in within minutes, then preserved for 6 to 12 months with minimal loss in quality. Everything will be revealed right now. Once considered a cheap, nameless fish, few people realize that pollock is quietly feeding the world, with an annual output of over 3 million tons. Even more remarkable, more than 90% of this volume is frozen almost immediately after leaving the water, turning the ocean into a massive, industrial-scale freezing line. As soon as they are brought on deck, the fish are dumped into the intake hopper and fed directly into the vessel through an enclosed conveyor system, operating continuously at speeds of 1 to 2 meters per second. A circulating cold seawater washing system not only removes slime and impurities, but also rapidly lowers the core temperature to near 0 degrees Celsius within minutes, effectively halting decomposition from the very beginning. From here, they move straight into a filleting machine, where high-speed blades rotate with remarkable stability, precisely aligned along the body axis. The thin, razor-sharp blades split the fish along the natural grain of the muscle, minimizing damage and preserving the integrity of the flesh. Immediately after splitting, the flesh passes through a skinning system, where thin blades run tightly along the surface, before moving on to a pin bone inspection stage under high-intensity backlighting to remove any remaining bones. After the final cleaning step, each piece is sorted to precise size and thickness, then placed onto metal trays and fed into a plate freezing system at around 35 degrees Celsius. Here, chilled plates press tightly from both sides, transferring cold directly into the product at extremely high speed, allowing the core temperature to drop rapidly within a short time. Thanks to this contact freezing mechanism, the entire structure of the flesh is effectively locked almost instantly, minimizing the formation of large ice crystals and preserving the firmness, color, and original quality of the fish. Once out of the freezing chamber, the product undergoes a rapid inspection before being sealed and transferred into a continuous cold chain. This entire closed-loop process is typically completed in under 2 hours, shorter than a domestic flight, yet enough to transform freshly caught fish into a globally distributed commodity. At the next stop, we step into a frozen patty production system, where thin slices of meat just a few centimeters thick are produced at industrial speed, forming a critical link in the nearly $760 billion global hamburger industry each year. The journey of a burger patty doesn't begin on the grill. It starts at the meat selection stage, where structure, juiciness, and texture are already determined from the outset. To create patties that are tender and flavorful, factories don't rely on random cuts, but instead use carefully calculated blends. The shoulder maintains structure during cooking, the brisket enhances juiciness, and about 15 to 20% natural fat helps retain moisture within each fiber. After being sliced, the meat blocks move directly into industrial grinders, where a rotating screw applies high pressure to push the meat through perforated plates of standardized size, forming uniform strands. The grinding speed is tightly controlled to minimize heat buildup, preserving both color and protein structure. Once the meat is processed to the desired particle size, the mixture is transferred to a blending system where oil, salt, pepper, onion powder, and moisture-retaining and binding additives are incorporated in precise ratios. creating a uniform mixture ready to move directly into the patty-forming machine. In this section, each portion of meat is fed into a forming machine, where circular molds press down with gram-level precision, ensuring uniform weight and thickness. At the same time, the signature surface grooves are stamped directly onto the patty, allowing heat to distribute evenly during grilling and preventing edge curling on surfaces exceeding 200 degrees Celsius. Immediately after being cooked, the patties enter a rapid cooling stage, where powerful streams of cold air are blasted directly onto the surface, bringing the temperature down in an instant. At the end of the line, automated robots pick, weigh, and seal each portion within seconds, ensuring consistent portion control and airtight packaging. These precisely handled patties are then transferred seamlessly into a continuous cold chain, ready to be distributed across the global hamburger supply network. With a water content of up to 90%, fresh strawberries are among the most perishable fruits, leading to significant waste if not handled properly. That's why frozen strawberries have completely changed the game, extending shelf life from just 6 days to up to 6 months, turning a delicate crop into a highly profitable commodity. Unlike conventional handling, strawberries in industrial processing skip the initial washing stage and move straight into the de-stemming machine, where each berry is guided and precisely positioned before the dirtiest part is removed in a single motion. The cutting blade cleanly separates the stem along with the area most prone to microbial contamination, fast enough to preserve the fruit's fresh, original state before any quality degradation can occur. Immediately after, the strawberries enter a recirculating washing system, where cold water combined with air agitation penetrates every tiny pore on the surface, removing dirt and residues without damaging their fragile structure. As soon as they leave the wash tank, they don't pause. Instead, they are instantly dried using vibration and cold air, stripping away surface moisture within seconds and creating ideal conditions for the next stage. From here, the entire flow moves directly into IQF freezing at -4 degrees Celsius, where each berry is individually frozen within minutes, preserving its shape, color, and juiciness as if freshly harvested. Once stabilized, cameras and sensors rapidly scan the product stream, removing any substandard pieces before packaging. By the time they leave the line, the strawberries are fully stabilized, sealed, and transferred straight into a continuous cold chain, ready to travel thousands of kilometers with virtually no loss in original quality. As the world's most widely produced tropical fruit, up to 80% of exported mangoes never reach fresh fruit shelves, but instead move straight into industrial freezing lines just hours after harvest, forming a global value chain worth over $3 billion each year. Right after leaving the orchard, mangoes don't go directly into freezing. Instead, they pass through a high-speed cleaning station where pressurized water jets at around 2 to 4 bar continuously remove dirt, sap, and microorganisms from the surface within just 2-3 minutes, while the washing water is recirculated and filtered through multiple layers. From there, the fruit moves onto an optical sorting conveyor, where industrial cameras instantly analyze color, size, and ripeness to select only those suitable for freezing. After passing the sorting stage, each mango is secured on a specialized holder to maintain a stable position throughout processing. High-speed rotating blades then peel off the skin within seconds, closely following the fruit's curved surface while preserving nearly all of the flesh inside. Thanks to this level of precision, material loss is significantly reduced, saving around 15% compared to manual peeling methods. Immediately afterward, synchronized gripping mechanisms and cutting blades separate the two thick cheeks in just 1 to 2 seconds per fruit, sliding them directly onto the next conveyor. The remaining flesh around the seed is not wasted but collected separately to produce puree, juice, or diced frozen mango, recovering an additional 10 to 20% of raw material value within the same processing line. Next, the mango may undergo a brief blanching step or move straight into deep cold airflow at around -35°C to -40°C, where the temperature drops rapidly, forming ultra-fine ice crystals that preserve juiciness and cellular structure. Finally, the product is immediately transferred into sealed packaging and enters a continuous cold chain, completing the entire process. Leaving the mango factory behind, we arrive at a frozen broccoli plant, an industry generating over $5 billion annually and accounting for nearly 75% of the global broccoli market. The journey of frozen broccoli begins as each head is placed onto a cutting conveyor, where rotating blades calibrated to standard sizes quickly separate the thick stalk from the florets within seconds, producing uniform pieces from the start. From here, the florets move directly into a recirculating wash tank, where water at controlled pressure removes soil and insects while preserving the delicate structure. Immediately after cleaning, the broccoli is transferred to a blanching tank at around 95°C for nearly 2 minutes, a step that locks in the vibrant green color and halts enzyme activity that could degrade quality. Once the heat is removed, the product moves straight into a deep freezing chamber at approximately -40°C, where each piece is individually frozen within minutes, locking in its natural moisture, shape, and crisp texture while preventing cellular damage and quality loss. Finally, the broccoli is sealed in airtight packaging and enters a continuous cold chain, carefully maintained at stable low temperatures, ensuring it can travel long distances and still arrive in kitchens worldwide, from supermarkets to family tables, without losing its freshness. For most fruits on the market, deep freezing is essentially the end of any fresh structure. Yet, blueberries are a rare exception, almost paradoxical, because in many cases their frozen form can retain nutrients even better than those sold as fresh. And to produce frozen blueberries, the fruit doesn't pause at any intermediate stage but flows immediately into a continuously moving wash stream where fine dust and field residue are removed within the first few seconds. Right after that, as the berries spread across a bright conveyor ahead, workers positioned along both sides quickly remove any remaining stems and leaf fragments, a seemingly small task that must be performed with precision at speeds of thousands of berries per minute, ensuring the entire downstream process never gets quality bottlenecks from the very start. As the process moves into sorting, each blueberry no longer simply travels along the conveyor, but is inspected by high-speed camera systems operating 20 to 40 times faster than the human eye, continuously scanning tens of thousands of berries per minute to detect even the slightest color deviations that are nearly invisible to manual inspection. Infrared sensors can even read the internal condition of each berry, identifying those that are beginning to soften from the core, before compressed air jets react within milliseconds to instantly remove them from the product stream. Because a single defective berry slipping through could compromise an entire batch of frozen blueberries downstream. Immediately after sorting, the blueberries enter the stage that determines overall quality, rapid freezing at around -35 to -40°C. The berries are spread into a thin layer on a conveyor, while high-velocity cold air flows through the gaps, extracting heat almost instantly. Within just minutes, the core temperature drops low enough to lock the cellular structure, preventing the formation of large ice crystals that could rupture cell walls. Thanks to this ultra-fast freezing rate, blueberries retain their plumpness, natural color, and flavor almost unchanged after thawing. After freezing, the berries pass through a multi-level vibrating screening system, where each piece is fully separated to meet IQF, individual quick frozen standards. Clumped or undersized berries are removed, ensuring complete uniformity. Next, the blueberries are rapidly transferred into a deep chilled packaging area where they are portioned, dehumidified, and sealed within minutes. The entire process runs continuously, allowing each berry to preserve its just harvested quality, ready for global distribution. While Brazil holds more than 230 million cattle, a vast living reservoir, the United States takes a completely different approach. Not raising more, but transforming meat into value. Each year, over 200,000 tons of beef are dried and condensed into convenient jerky, traveling across interstate highways to convenience store shelves around the world. Few people realize that beef jerky is one of the oldest forms of portable protein, dating back more than 2,000 years, beginning when the Inca hung meat in the cold winds of the Andes. Since then, these small strips have moved through history, spreading across continents and becoming a globally consumed food. Beyond its historical value, these thin slices function as a compact biological energy source, where protein is concentrated to levels that can be up to 3 times higher than eggs and far exceed fresh meat, which still retains water. As a result, each strip becomes a refined form of energy, dense, efficient, and quickly absorbed by the body. And to turn those small strips of meat into a massive multi-billion-dollar industry, everything doesn't begin in factories. It starts on the farms. Right now, let's head to the Texas Panhandle, one of the largest beef-producing hubs in the United States, where each animal is not just raised but monitored like a mobile data point. Here, cattle don't simply grow, they emit signals. From movement patterns and daily feed intake to the slightest behavioral changes, everything is continuously recorded through chips and sensors, allowing control centers hundreds of kilometers away to track thousands of animals in near real time. Across grasslands stretching to the horizon, breeds like Angus and Hereford develop steadily before entering feedlots, the acceleration phase, where diets are no longer left to nature but are precisely calculated down to the gram. Ground corn, energy-rich byproducts, and trace minerals are mixed within minutes, yet enough to feed hundreds of cattle per batch. As feed trucks move along the troughs, rations are laid out in continuous lines, synchronizing feeding behavior across the herd and maintaining consistent daily weight gain. Interestingly, even what seems like waste, such as melon rinds or corn cobs, is recycled into usable energy. Every day, tons of byproducts are reintegrated into the system, reducing waste and optimizing costs. And when everything connects, what emerges is no longer traditional farming, but a vast, data-driven production system. After approximately 120 to 180 days of finishing, once each living data point reaches its optimal threshold, the journey doesn't stop. It shifts into the next phase: transportation. The cattle are guided through narrow, curved chutes that leverage their natural instincts, allowing them to move smoothly while minimizing stress before loading. Transport trucks are divided into multiple, ventilated compartments with anti-slip steel flooring to maintain stability over distances that can reach up to 500 kilometers. And just minutes after each trip, every compartment is thoroughly cleaned, ready to continue the next cycle, a continuous flow with virtually no downtime. Leaving the grasslands after a journey of hundreds of kilometers, the cattle enter the most critical stage of the production chain, the processing facility. Almost immediately, the carcass is transferred onto an industrial splitting line, where a high-speed saw, operating at up to around 3,000 revolutions per minute, precisely cuts along the spinal axis within seconds. From here, each half is separated and moved into subsequent stages of sorting, trimming, and processing, where every cut is directed toward specific uses across the entire production chain. As soon as it leaves the main processing area, the carcass is transferred to the cutting stage, where raw materials are specifically prepared for beef jerky production. Here, the meat is not cut randomly, but separated along the natural grain direction to preserve muscle structure, a key factor that directly influences shrinkage and shape during drying. First, muscle groups from the shoulder and upper chest are prioritized, as they contain long, relatively uniform fibers, forming the foundation for jerky pieces that retain a stable shape after drying. Next, selected portions from the hind leg, rich in natural collagen, are incorporated to create the characteristic chewy and elastic texture. At the same time, the meat is inspected for color and lean ratio to ensure freshness and consistency before moving on to fat trimming and marination in the next stage. At this transition point, the production line moves into the trimming stage, the quality shield of the entire beef jerky process. Trimming always begins with the removal of nearly all visible fat, because even a thin strip just a few millimeters thick can significantly shorten shelf life after drying. The reason lies in the fact that lipids in fat oxidize much faster than lean meat proteins, leading to rancid odors and reduced product quality. For this reason, workers carefully remove the white fat layers, while also eliminating coarse muscle bundles, large tendons, and dense connective tissues, to retain only the most structurally stable meat. At this stage alone, up to 15 to 20% of the initial mass may be removed, but in return, it creates the foundation for clean, chewy beef jerky that can be stored reliably for months. After trimming, the meat is fed into a multi-blade industrial slicer, where continuously rotating blades cut along the natural muscle grain, producing slices with a near gold standard thickness of 4 to 6 millimeters. This precise thickness allows the jerky to form clear fibers after drying, maintain a clean shape, and achieve the characteristic chewy texture without becoming overly dry or brittle. Following slicing, the meat strips may be rinsed and briefly blanched in hot water for about 1 minute to clean the surface, reduce microbial load, and slightly firm up the muscle fibers. However, this step depends on the production facility and is not mandatory in all beef jerky processing lines. After the removal of fat and tough connective tissues, the meat immediately enters the flavor-locking stage, a critical step that defines each brand's identity. Inside vacuum tumblers, salt, sugar, pepper, garlic, and soy sauce penetrate deep into the muscle fibers within just 20 to 30 minutes, then building a rich flavor base before drying. It is at this stage that each producer holds its own secret formula. Jack Link's leans toward a bold, savory profile typical of classic American-style jerky, while Old Trapper stands out with its signature lightly sweet, smoky flavor. After seasoning, each batch of meat is placed into sealed stainless steel tumblers, rotating at dozens of revolutions per minute. This continuous motion ensures the marinade doesn't just coat the surface, but begins penetrating deep into the muscle fibers. The real game changer, however, lies in the mechanical needle tenderizing stage. Within just 5 to 10 seconds, hundreds of fine needles pierce the surface, creating pathways that allow the seasoning to reach deep inside the meat. Depending on the facility, the marination process may be repeated 1 or 2 more times, effectively forming a multi-layer flavor lock, so that by the time the meat enters the drying chamber, the richness is no longer just on the surface, but fully embedded within every fiber. After marination, the meat slices are not simply loaded into the dryer. They must be carefully arranged layer by layer, almost like a thermal map, to ensure each piece dries evenly down to the millimeter. The slices are spaced about 3–5 millimeters apart, allowing hot air to flow across the entire surface. Even a slight misalignment in a single tray can cause an entire batch of hundreds of kilograms to dry unevenly. Because inside an industrial dryer, air is the true chef behind beef jerky. In some production lines, instead of laying the meat on trays, the strips are hung vertically on stainless steel rods using metal hooks, allowing hot air to circulate evenly around both sides at the same time. Once the meat is neatly arranged on trays, the entire batch is transferred into the drying chamber. From that moment on, the meat never touches direct flame. Instead, it enters a tunnel of hot air, where temperature is precisely controlled down to each degree Celsius. Streams of air at 50 to 70 degrees Celsius continuously pass through every layer of meat for 6 to 10 hours, drawing moisture out from each muscle fiber. By the end of the process, the meat can lose up to 60% of its original weight, and it is at this point that fresh meat is truly transformed into beef jerky. After leaving the drying chamber, the jerky strips may retain their signature long form. However, in some brands such as Jack Link's, they continue through an industrial cutting system where the strips are processed within seconds into uniform snack-sized pieces of around 2 to 5 centimeters, ready to move onto high-speed packaging lines. After leaving the sizing stage, the beef jerky moves into the final packaging process. Here, each bag is inflated with clean air to maintain its shape before receiving the product. Within seconds, the jerky is filled in standardized portions of 30 to 50 grams per bag on high-speed packaging lines, while workers perform quick checks on color, dryness, and weight to ensure batch consistency. Immediately after, the bags are vacuumed and fully sealed, creating a stable environment that limits oxidation and preserves the product's characteristic flavor. This seemingly simple step acts as the final lock of the entire process, allowing the jerky to be stored for 6 to 9 months while maintaining its chewiness, aroma, and fibrous structure almost intact. Few people realize that the billion-dollar empire behind Ferrero Rocher actually began as a historic escape from a cocoa shortage. In the aftermath of World War II, when Europe's economy was severely strained, Pietro Ferrero made a bold decision, replacing much of the scarce cocoa with hazelnuts, an abundant resource in Piedmont. The result was gianduja, a dense block of hazelnut chocolate wrapped in foil and sliced like bread. From a modest family pastry shop, Ferrero grew to control up to 25% of the world's hazelnut supply, generating over $18 billion in annual revenue. Even more surprising, behind those iconic golden-wrapped chocolates lies an exceptionally secretive operating system, often regarded as one of the most discreet organizations in the food industry. Building on the massive success of Nutella and later Ferrero Rocher, the Ferrero family rose into the ranks of the world's wealthiest, with their fortune at times surpassing $100 billion, occasionally overtaking tech giants like Mark Zuckerberg and Michael Dell during downturns in Silicon Valley stocks. To sustain this massive money-making machine, Ferrero relies not only on secret recipes, but on absolute control at the very source of its raw materials. Through a network of plantations stretching from Chile to South Africa, the group has acquired major suppliers in Turkey, the world's leading hazelnut producer, to ensure a year-round supply from both hemispheres. Here, each hazelnut tree is planted at precise densities to optimize sunlight exposure, begins bearing fruit in its 5th year, and maintains stable productivity for up to 4 decades. Although often associated with the warmth of winter flavors, hazelnuts are in fact a peak of summer crop, ripening in August. This narrow harvest window demands exceptional speed, as even a single heavy rain can wipe out an entire year's yield if the nuts are not collected in time. On flat hazelnut plantations, farmers can rely on a single sweeping machine to cover dozens of hectares, completing the entire collection process in just one pass. Built around two continuously rotating rubber brush systems, the machine glides across the ground, gathering hazelnuts into long, straight windrows. Secondary sweeping arms then consolidate the nuts and direct them into a storage hopper for collection. While this approach significantly reduces manual labor, its main limitation lies in its coarse mechanical nature. The machine can easily miss nuts trapped in uneven ground depressions or areas with inconsistent surfaces. In addition, sweeping directly over dry soil often pulls in large amounts of stones, twigs, and debris, while generating heavy dust clouds, placing considerable strain on the downstream cleaning process. Solving this challenge at its core, a new era has emerged with modern vacuum harvesting machines, operating like giant industrial vacuum systems mounted behind tractors. Instead of sweeping, operators control flexible suction hoses ranging from 25 to 50 meters in length, capable of reaching every corner within a 100-meter radius. Powered by high-pressure airflow, these systems can lift hazelnuts from a distance, enabling near-complete collection even when the nuts are buried beneath leaf litter or trapped in ground crevices, areas where conventional sweepers are virtually ineffective. More impressively, in a single pass, the machine performs 4 integrated processes: suction, shell separation, cleaning, and bagging. With the support of auger systems and dual-fan airflow, up to 98% of impurities are removed on the spot, allowing a single machine to replace the labor of up to 35 workers. The result is a stream of perfectly cleaned hazelnuts, ready to enter Ferrero's proprietary processing chain, where these raw materials begin their transformation into one of the most valuable, liquid gold ingredients in the global confectionery industry. After harvesting, the sacks of hazelnuts are transported directly into a closed-loop production system, officially triggering a highly confidential transformation process. Notably, most of the machinery here is designed and manufactured in-house by Ferrero, creating a critical technological barrier that makes it nearly impossible to replicate the brand's signature multi-layered chocolate structure. Upon arrival at the factory, streams of raw hazelnuts are discharged onto heavy-duty conveyor belts to initiate a multi-stage cleaning process. First, they pass through industrial rotary screening drums, massive stainless steel cylindrical cages equipped with progressively smaller mesh sizes. These machines operate based on the combined principles of centrifugal force and gravity. The drums rotate at a stable speed of 15 to 20 revolutions per minute, precisely calibrated to allow impurities, broken shells, and defective nuts to be expelled through the mesh openings without damaging the delicate skin of high-quality kernels. With a processing capacity of up to 5 to 8 tons per hour, this system ensures that only uniformly sized hazelnuts, meeting strict diameter standards, are allowed to proceed to the next stage of deep processing. Next, the hazelnuts enter the roasting stage, a critical turning point that unlocks their natural oils and creates the signature crunch. The entire process is carried out in small batches within hot air circulation ovens, where infrared sensors continuously monitor and maintain temperature with precise control at every degree. At this stage, even a deviation of just 15 seconds can shift the flavor from rich and nutty to bitter and burnt, enough to ruin an entire batch worth thousands of dollars. Immediately after roasting, the hazelnuts are sorted. The most perfectly round and intact nuts are reserved as whole centers, while the remaining ones are directed into grinding systems to produce the finely crushed hazelnut coating used for the outer layer. While the hazelnuts are being prepared, a parallel production line begins crafting the liquid core, the true soul of each chocolate. The creamy filling is an ultra-smooth blend of ground hazelnuts, sugar, cocoa powder, and vegetable oil. This mixture is fed into high-speed homogenizers to refine its texture, ensuring that no graininess is perceptible on the palate. It is then stored in temperature-controlled jacketed tanks, where viscosity is carefully maintained, fluid enough for automated pumping, yet thick enough to hold its shape once cooled. At the same time, in the coating section, massive blocks of pure chocolate, each weighing dozens of kilograms, are loaded into large-scale bain-marie melting systems. With a capacity of up to 2.5 tons of liquid chocolate, these units circulate hot steam around the vessel walls, gently melting the chocolate to preserve its glossy texture and prevent any risk of scorching. If chocolate is the soul, then the wafer shell is the structural frame that delivers the unmistakable crunch. The process begins with tens of tons of refined wheat flour, mixed with water and vegetable fats in 300-liter industrial mixers. The resulting batter is then precisely injected into hemispherical metal molds and sent through high-pressure gas baking systems. Within seconds, carefully controlled heat transforms the liquid batter into rigid wafer half-shells. Immediately afterward, an automated nozzle system fills each half-shell with hazelnut cream. At the next station, robotic arms place a whole hazelnut at the exact center of one half-shell. The two halves are then aligned with precision down to fractions of a millimeter and sealed together using a centering device. The result is a perfectly spherical wafer, enclosing a rich core of cream and a whole hazelnut. Interestingly, Ferrero spent nearly 5 years experimenting to perfect this spherical wafer structure, thin and light, yet capable of preserving the smooth cream inside without moisture compromising its crispness. After cooling, the wafer spheres enter the enrobing system. Here, they travel along a mesh conveyor and pass through a continuous curtain of liquid chocolate, maintained at a precisely controlled temperature, ideal for keeping the chocolate perfectly fluid without melting the hazelnut cream inside. While the chocolate coating is still wet, the candies move through a vertical sprinkling system that evenly distributes roasted hazelnut fragments over the surface. To achieve the signature rough texture without distorting the spherical shape, the conveyor is equipped with a low-frequency vibration mechanism that removes excess coating. Finally, the coated chocolates are transferred into a deep cooling tunnel for approximately 10 to 15 minutes. This stage solidifies the structure and locks in the crisp texture, preparing the products for the final packaging process. After exiting the cooling tunnel, the final stage begins with the iconic gold foil wrapping. As each chocolate enters the center of the wrapping unit, rotating grippers gently hold it in place, while synchronized mechanical arms pull and conform the aluminum foil tightly around its spherical surface. Instead of a single pressing motion, the system performs a rapid sequence of twisting, folding, and tightening, allowing the foil to seal perfectly around every contour in just 0.1.2 seconds, without deforming the delicate wafer shell inside. Immediately afterward, a secondary rotating mechanism twists the excess foil at the top, forming the signature peak. The finished chocolates are then released onto a chute, with throughput speeds ranging from several hundred to over 600 pieces per minute. In reality, the iconic gold foil is not merely decorative, it acts as a barrier against oxygen and light, preserving the stability of cocoa fats and the freshness of hazelnuts, while preventing rancidity and flavor loss caused by humidity. To create a perfectly melting Kraft single slice, everything begins with ingredient selection, where base cheese blocks such as cheddar, Colby, and other semi-hard cheeses are carefully chosen. Once the ingredients meet the required standards, the cheese blocks are transferred onto the processing conveyor and enter the grinding stage, where the breakdown of structure is controlled down to the finest detail. At this stage, the cheese blocks must be kept in a solid state to prevent phase separation of fat and protein prior to emulsification. Industrial blades rotate continuously to break the cheese blocks into smaller pieces, increasing surface area and preparing the material for the subsequent emulsification cooking step. At the same time, air becomes the invisible enemy of the entire process. If oxygen is drawn in during grinding, it can trigger oxidation reactions, altering flavor and disrupting the color that must remain stable. For this reason, the grinding system is designed to be nearly fully enclosed, minimizing air intrusion and keeping the cheese in an absolutely stable state before it moves on to the next stage. With traditional cheese, shelf life after opening typically lasts only 5 to 7 days. In contrast, Kraft singles can remain stable for 30 to 60 days in the refrigerator. This difference does not come from magic, but from the step where emulsifying salts and water are added, and the mixture is cooked in a continuous system for just a few minutes. Here, the cheese transitions from a solid, separated, and difficult-to-control state into a molten form, ready to be shaped and transformed into millions of Kraft singles slices. After melting, the cheese is poured into molds, where it solidifies again under controlled temperature and pressure, forming uniform blocks ready for the cutting stage. From these formed blocks, the processed cheese is sliced into standard pieces of approximately 9 × 9 centimeters, only a few millimeters thick, using high-speed cutting systems operating continuously. Immediately after cutting, each cheese slice is wrapped in a thin film to secure its shape, then sent directly through a controlled cooling water bath. The cold water rapidly lowers the temperature, locking in thickness and cut edges before the slice has a chance to spread or warp, while also bringing the temperature down to a safe range so the subsequent wrapping process can proceed smoothly. The entire cycle is completed in approximately 30 seconds, using a circulated water system that is sterilized and closely monitored, ensuring that each slice retains its structure without absorbing water. This practice of individually wrapping each slice during the cooling stage is a distinctive feature of Kraft's production line. Rather than allowing the cheese to fully stabilize before packaging, Kraft fixes the shape and state of each slice within the thermal process itself, ensuring high uniformity, easy separation, and consistent quality in use, an approach that is critical for large-scale industrial production. After the cooling stage, the slices are transferred directly to the automated packaging area, where pick-and-place robots handle the entire operation. Mechanical arms move along precisely repeated paths, lifting each slice, placing it into trays, and aligning positions before sealing, at speeds that can exceed 200 slices per minute. Human workers only supervise and perform random inspections, while consistency, hygiene, and production pace are entrusted entirely to machines, fast, precise, and tireless. Farewell to Kraft singles and the familiar rich, creamy cheese slices. Up next, we turn to butter, the strategic pillar of the global dairy industry. To produce butter, everything begins with fresh milk, a familiar raw material that is strictly controlled from the very first moment. When tanker trucks arrive at the plant, the milk is pumped directly into stainless steel silos within a closed system, with minimal exposure to air. Temperature is kept stable from farm to factory to prevent oxidation and bacterial growth. Before entering production, the milk must pass a series of tests: fat content, pH, microbiological levels, antibiotic residues, and impurities. A single deviation is enough for an entire truckload to be rejected, because in butter production, quality always takes precedence over yield. Milk that has met quality standards is gently warmed and fed into a centrifugal cream separator. At speeds exceeding 7,000 revolutions per minute, the lighter fat fraction is separated as cream, while the remainder becomes skim milk. The cream remains liquid, fat-rich, and serves as the core ingredient for subsequent churning and butter production. After being pasteurized at approximately 85 to 90 degrees Celsius for a short period and aged at 5 to 10 degrees Celsius for several hours, the cream remains in liquid form and is transferred directly into an industrial butter churn, where the transformation truly begins. Under continuous agitation, the fat structure breaks down. The cream gradually thickens, then small butter grains appear and aggregate together. The liquid separated during this process is buttermilk, commonly used in food processing, while the butter in granular form is collected and prepared for the subsequent processing stages. Immediately afterward, the butter mass is washed with cold water at 5 to 10 degrees Celsius to remove nearly all remaining buttermilk, a critical step that determines the product's shelf stability. If buttermilk is not thoroughly removed, the butter can turn sour within just a few days. When properly handled, however, the butter can maintain its quality for many months. Next, the washed butter is transferred to specialized working machines. Through controlled pressing, folding, and mixing, the butter gradually transitions from a loose, non-uniform granular state into a cohesive, smooth, and pliable mass, with moisture evenly distributed throughout. At this stage, the butter reaches a fat content of 80 to 82%, meeting global commercial standards. Finally, the butter is formed into small retail blocks or large units of 20 to 25 kilograms and even 200 to 500 kilograms for industrial kitchens. Batches of butter weighing more than an automobile. Just minutes later, the butter enters the most demanding area of the factory, the packaging zone, where temperatures are constantly maintained at 10 to 15 degrees Celsius, nearly as cold as a meat storage facility. Here, speed is no longer an advantage but a matter of survival. If the line runs 3 to 5 seconds slower than designed, friction and ambient heat alone are enough to soften the butter's surface and cause deformation before sealing can occur. Packaging, therefore, serves more than a protective outer layer. The factory uses multi-layer materials coated with polymer or thin aluminum to block light and foreign odors. Even a minor deviation can cause the butter to lose its aroma and decline in quality within just a few weeks. Before shipment, the butter undergoes final quality checks on packaging integrity, weight, shape, and sample analysis to ensure compliance with standards. If Chinese people cannot live without chili oil, Americans can hardly enjoy bread without peanut butter. Each year, the United States consumes approximately 152,000 metric tons of peanut butter, averaging about 2 kilograms per person, generating a multi-billion-dollar market annually. The first step in peanut butter production is washing the peanuts, where dirt and impurities are removed and underweight or damaged kernels are separated. Only peanuts meeting structural and weight standards proceed to the next stages. The first step in peanut butter production is washing the peanuts, where dirt and impurities are removed and underweight or damaged kernels are separated. Only peanuts meeting structural and weight standards proceed to the next stages. After roasting, the peanuts are immediately transferred to a critical refining stage, skin removal, a step that directly determines the color and flavor of the final peanut butter. Here, the kernels pass through a modern skin removal system, where compressed air at 6 to 8 bar, combined with ultrafine grooved rollers, strips away the thin skins without breaking the kernels. Even a small amount of residual skin can introduce slight bitterness and darken the color, noticeably affecting smoothness and richness. Next, the peanuts move along a vibrating conveyor with high-power suction fans to remove any remaining skin fragments. This process also cools the kernels naturally, preventing overcooking before grinding. Before milling, the peanuts pass through an optical sorting system. High-speed cameras scan 5,000 to 7,000 kernels per minute, detecting burnt, discolored kernels or foreign matter, and ejecting them instantly using compressed air. When peanuts enter the rotary grinding system, high-speed shear and friction release natural oils, forming a smooth, golden paste without dairy ingredients. Heat from grinding improves flow before stabilization. Salt, small amounts of sugar, or vegetable oil are then added in precise proportions to refine flavor. The mixture is heated to about 180 degrees Fahrenheit to stabilize structure, reduce bacteria, and extend shelf life, with low moisture and high oil content, minimizing the need for preservatives.